So let's move on. Now we have Rodrigo Teixeira with us. He is actually coming from Delft, Netherlands. However, he joined to the CITCEA recently as a postdoc for 1 year. So he is Delft End here. And he will talk about North Sea Transnational grids.
Thank you, Professor Sumper, for the kind introduction. Also, I'd like to thank Professor Gomes for letting me the opportunity to tell you a little bit about the North Sea Transnational Grid project, which was the project in which I did my PhD studies. And, well, a little bit of like a subtitle for the project is a better way to integrate large-scale offshore wind power, and I hopefully to convince you about it. I would also like to acknowledge a colleague, which is not here, Edwin Winkelinghausen. He's one of the senior researchers that worked for the North Sea Transnational Grid project. He's with ECN, which is the Energy Research Center in the Netherlands, and some of the slides in these presentations were made by him, so it's a good thing to acknowledge. The structure of these is just to show you a little bit on the objectives and on an overview of what the project was about. And then I will cover some of the work packages in this project. The first two, more or less, are about social and economic benefits of the North Sea Transnational Grid, and a little bit also about the integration of these multi-terminal DC into the AC systems. So what is the impact on the AC systems? Obviously, looking from a Dutch perspective, since the project was developed and performed there. And then I'll move on to talk a little bit about multi-terminal DC network operation and control, a little bit of overlap with what my colleagues here at CITCEA already presented, where we show some results that we obtained in the Netherlands, and though some of the conclusions talking about the technical challenges that we see today before these multi-terminal DC networks can finally be successfully developed. So a little bit on the project's objective. The North Sea Transnational Grid wished to be a roadmap for the decision makers in Europe about how to approach the development of multi-terminal DC networks. So the idea was to provide modular and flexible and cost-effective solutions for the North Sea Transnational Grid, which in the beginning, when they were talking about it, they were not sure whether the multi-terminal DC network was the right solution. So they were still comparing point-to-point AC connection of offshore wind farms against the multi-terminal DC networks. I will talk a little bit about that. So here are the whats. The whats the project wanted to research. So it was basically what are the costs, benefits, and policies and regulations needed for this DC network to appear, and then move on to what are the effects on the AC systems, and then see how can we control and operate a mesh DC grid. And here a little bit on the whys. Today in Europe, the offshore wind energy is very, very rapidly growing. We have seen a growth of about 280% compared to install levels in 2010. So today we have 6.5 gigawatts of commissioned offshore power plants, and we have 4.5 gigawatts under construction. So we're thinking that about the end of 2015 we'll have 11 gigawatts of offshore power in Europe. And the predictions, they vary a little bit according to the person who is giving the prediction. So for instance, if you go to EVIA, which is obviously a wind energy lobby, they will tell you that lots of offshore wind will be installed in Europe, and sometimes they even mention up to 150 gigawatts by 2030. And we see that if the industry keeps growing rates, which sort of are at the minimum that have been seen so far, is about 8% per year, we will still see some 60 gigawatts of offshore power by 2030. So that's very significant amount of power, and we have to think what's the best way to integrate it. Then obviously find the most flexible, reliable, and cost-efficient solution for not only integrating the wind, but also allowing cross transport and markets within Europe. And see if then the multi-terminal DC networks are the solution, how can we use it to support the AC grids. Because in the end, what we really want to accomplish with electricity is deliver power to loads. So the DC grid would just be a vector to allow that to happen. A little bit on the data of the project. It started in 2009, so at the time it was a quite visionary project. Had 7 work packages, as I said, ranging from social and technical and economic aspects. Was fully Dutch financed. At the time, there were a lot of still large amounts of money for research coming from national governments, especially in the Netherlands. It had 5 PhD students, 2 postdocs, 3 senior researchers, which were basically managing the project at ECN, which is the energy company in the Netherlands, 2 full professors, and in the end, it reached very fulfilling results, and we have about 30 publications that are available on the website, nsdd-project.nl, and I invite you to look at it. And, sorry, this one. Basically, what we're seeing here is sort of the North Sea Transnational Grid project view of what the North Sea Transnational Grid would look like. Different companies and research institutes have different ideas, but this one is actually based on some assumptions. And the assumption is that we will have about 60 gigawatts of power according to national targets. There are grid reinforcements according to the 10-year planning of the TSOs of Europe. Each dot that you see here is about 1.1 gigawatt wind power plant. And they have full rated grid connection, so you are able to export the power of these power plants to shore. When we started with this project, the ratings of voltage source converters were about 1 gigawatt, so that's why it had this in mind. Today we could sort of rerun the whole project with 2.6 gigawatts and check again what the results would be. But basically we also consider that the cross-border through the DC ring is the same as the installed power of the offshore wind farms. Then I'll cover a little bit on the cost, benefits, and social economics, but the basic take-home message of the cost-benefit analysis is that we're better off integrated. So here you see a case 1 for the phase 1 of the project. And before we reach the network that I've shown, we considered 10 steps. And this was sort of the first step in which you have a linear radio network very close to the countries, and you connect the offshore power plants to this DC grid and then the DC grid to shore. So we call this the interconnected scenario, where the wind farm connections are made in DC. And then case 2, which was called separate scenario, in which the offshore wind power plants are connected with business as usual with AC lines, and then compare the two. So you can see that basically we're expecting that capital expenditures, CapEx, and levelized transmission costs are better when we consider the North Sea Transnational Grid. So here you can see a comparison of both in millions of euros, depending with the case. And the integrated case have lower CapEx. That's excluding the wind turbines, this figure that I'm showing here. In terms of levelized transportation costs, is the same. We see that we're about at 1.5 euro cents per kilowatt hour for the case with integrated, and about a little bit more than 2 cents per kilowatt hour for the case where the wind farms are connected directly via the AC to shore. However, obviously, since we consider that the hubs had a limited capacity, the energy supplied was not the same. Energy supplied in the case where there were separate connections were higher, because then you're not also considering that you have more opportunity for trade within the multi-terminal DC network. But in the end, the main message is that we will have lower CapEx and lower levelized transmission costs if we go for the North Sea Transnational Grid. And today, with the higher VSC technology, we'd probably see more energy supplied from the transnational grid as well. Now, with the social welfare analysis, it looked at a little bit different scenarios. So I looked at 2 scenarios. One was called full ring, which the hub capacities are again close to 1.1, 1.2 gigawatts. And here you see here the blue dots, which are sort of conglomerates of offshore farms, and then they're connected to the AC grids via the DC lines and a meshed DC grid. And instead, you can consider that the same wind farms will be connected DC to their countries, but the connection between their countries will be done at business as usual with point-to-point. And we call this the full ring equivalent. So basically, as my colleague from the Friends of the Supergrid showed, there is a social welfare and a net benefit of the transnational grid if we looked at it in a 30-year lifetime. But this social welfare is not equally shared among the European countries. And then we can see here, for instance, Germany, Netherlands, and UK have actually negative net benefits, because if they are the ones that are bearing the costs for the grid, they're not getting all the benefits. Where there are other countries can benefit from the network. I'm not sure here why Spain is showing as a deficit due to the North Sea Transnational Grid. That's something actually that we can propose to panel. But in general, we can see that the social benefit for Europe together is positive and is about the same figure that was shown before, 1.7 billion euros for a case of low wind. So in the end, the conclusion is that the North Sea Transnational Grid is beneficial to Europe as a whole, but may not beneficial to the countries that are bearing the cost if they're left alone. So we need a solution, and we need to expand the scope of the ITC scheme, which is the inter-TSO compensation. We need to share benefits, but also we need to share costs. All right, now I'll talk a little bit about the AC grid planning and stability, also from a Dutch perspective. So this study was done with an AC model that is provided by TenneT. And anyone that's in this research field know how hard it is to get a very detailed European model of the AC network to do meaningful studies. So in the end, also the model provided by TenneT had low level of detail in UK and France, for instance. France may be not very problematic to have a low detail model, but UK it is, because together with Germany, they account today for 76% of the whole offshore wind market. So we need good UK models. Then, as we get closer to the Netherlands, we had better models. So we had modest models for Belgium and Germany, and very detailed model of the Dutch network. So then we could see what are the impacts of the offshore wind into the Dutch network. And then it analyzed 3 topologies for the DC network. One was individual wind power plants connected straight to different points in the country, so in the south, in Zeeland, in the middle, and in the north. Then you can connect these farms and sort of make a national part of the North Sea Transnational Grid, and then later on you have the full case 1 of the North Sea Transnational Grid, which in the future will then evolve into a mesh network. What we see here, looking at different snapshots of the unit commitment analysis, is that the size of the multi-terminal DC network can affect the AC unit commitment. So in the first case, you see that the conventional generation was about, I cannot see very well, 8.9 megawatts. I'm sorry, 8.9 gigawatts. And then as you move on to more integrated North Sea Transnational Grid, you need less and less the onshore generation. But if we take a look at the third case, and we look at the flows in the network in the Netherlands, we have basically 3 HVDC cables point-to-point with CSC technology, which we can control the power flow. So these are BritNed, NorNed, and the Cobra cable, and they have limited capacities. So more or less here, we see that we are dispatching them at the limited capacity, and what happens is that there can be a significant flow from the Netherlands to Germany and from the Netherlands to Belgium. And we need to be able to also control these flows on the AC system. But in the end, my colleagues doing the work on AC planning saw that up to 35 gigawatts of offshore wind can be connected from the North Sea Transnational Grid, and it won't disturb much the transient stability of the Dutch grid. It is true that AC disturbances will propagate from different AC grids to different AC grids, especially via the distributed voltage control of the multi-terminal DC network. And here is written especially for droop control, but it's actually for any distributed voltage control strategy. But we see that the AC system transient stability is insensitive to the multi-terminal DC network topology. It's just a matter of the power that's coming, but not much of the topology, because the AC system really is transparent to the topology of the DC grid by the converters. The converters fully decouple, for instance, in the case of offshore wind farms, the dynamics of the farms from the dynamics of the AC grid. So we have to ourselves plan very well what will be the role of the voltage source converters connected to the DC grid and to the AC grids at the same time. Important is that the onshore unit commitment influences the dynamics after a disturbance. So if we have less conventional generation because of a increased North Sea Transnational Grid, we have very well to look at what will happen after disturbances. For instance, one solution is to work with increased inertia, as Adria showed. Now a little bit more on the multi-terminal DC network and operation. This is the part where I did my PhD studies. So basically, we had two work packages. In the first one, the idea was develop the models that you need to study the dynamics of these systems. So basically, coming from left to right, we had a wind farm model, takes a wind speed and puts some power into a VSC station model. And this was done by ECN because they have thorough knowledge about mechanics, aerodynamics, and electric systems of offshore wind and onshore wind. Then we have a HVDC station model, a multi-terminal DC network model, then again another converter, which is the one that finally interfaces with the AC grid. And the idea here is that if you model your systems with very large amount of details, then you get a model that is very slow. So for instance, if for the HVDC converters, we didn't consider the switching characteristics of the converters because we were only interested in doing developing control. So basically, we wanted to evaluate the chosen transnational grid options with regard to grid codes, especially voltage dips, and we wanted to develop a voltage source controller for multi-terminal operation. So this is what actually we've done in the North Sea Transnational Grid. And what happens here is that I think we're a bit not in sync with what's being doing now in Europe. Everyone is pushing forward a lot for droop control. And I guess that back then we were thinking a little bit out of the box, and we went instead with PI regulators and an optimal DC power flow algorithm. So we're sort of combining the secondary and primary control that Augusti showed into one box, and we can left out the tertiary control for a droop control. But we are using actually PI controls. And the way that that works is that you can know the generation at offshore farms, send it to a load flow algorithm, have an OPF, then you can check if this OPF solution is N-1 secure and send voltage set points to the voltage source converters. And at the voltage source converters, we are using a PI regulator to control the square of the direct voltage, because that makes a linear control loop that is also faster and easier to regulate. So the idea basically is, if you know what the power that you would like in your network, you have to control your DC voltages. And the goal of this sort of control is that they have to be simple and fast, and they have to allow the system operator to have an operator insight into what is happening on the DC grid. So the transmission system operator doesn't really want to know what are the DC voltages on your DC network, but he's more interested in what are the power flows that you are getting on your DC network. So this is a high-level control design. It can be used to control the power flow inside the network, and it's capable of handling large networks as the one that I've shown here in this slide where we did simulations. All right, but simulations is not enough. You have to go down into the lab and test the system, so we did so. We built a multi-terminal DC network to test the models and control. And basically, we had two real-time controllers, one that was controlling 3 voltage source converters, and one that was emulating an offshore wind farm. And then at the bottom, I guess you can see here the connections of our 3-terminal DC network. For emulating the offshore wind farm, we had real data from a Dutch farm. It's the Egmond aan de Zee, and it is 20 kilometers offshore, has about 30 kilometer square area, and 110 megawatts more or less. ECN provided us with real power curves that were observed in this offshore wind farm in one day. Here I'm showing the time scale in seconds, but actually this was hours. And we had to scale down the time to be able to simulate it in the lab. And here you can see on the scope the wind power coming from one of the converters. So we're basically telling one of the converters that he's connected to this offshore wind farm, and he has to input this power into our grid. This is the topology of the network. So we're using a parallel radio topology with 3 converters, which is more likely to be the initial topologies that we'll see for multi-terminal DC grids. And basically, what we do is that we set these voltages here to obtain this power flow here. So I'm in the lab, the system operator, and I'm telling to my system that the power coming from the red curve here, which is the offshore wind farm, should be split between the 2 other voltage source converters, 1 and 2, according to the power scheduling that I'm giving. And in order to do so, you have to apply these voltages. Now, these voltages seem quite hectic if you're considering that they happened in a 240 second time frame, but actually you would have to think in 240 minutes. So they wouldn't seem to be varying the voltage a lot very fast. As a little bit of a push, I challenged my colleagues working with droop control to achieve this sort of voltage profiles to control their power flow very precisely to these levels. Obviously, this is the advantage of the method. The disadvantage is that in case of faults, you are not able to directly control how the converters share the power. So you would still need some sort of droop control, but maybe not at the secondary part, but at the tertiary part. So I guess we can actually benefit from combining the two strategies. Now, as a conclusion, I would like to show you some technical challenges that I see before we can get to a multi-terminal DC network in Europe that resembles something like this. To me, the least of the technical challenges, at least from the DC network perspective, is dynamics, because the converters are extremely fast. We can control currents to milliseconds, voltages and power into the hundreds of milliseconds. So if we apply all the knowledge we have in control engineering, I think we can solve dynamics issues very reasonably. Control, here it means really the control of the optimal power flow, and as Monica showed, now we are already moving to actually consider security constrained power flow. So also I think that power flow will be some of the challenges that we will also be able to tackle very fast in the beginning. But stability behavior of AC networks, which reply in much slower fashion than DC networks. The system integration that was spoken here before, different vendors with different control ideas, with different maybe even technologies, have to be integrated together before this system can happen. And then fault behavior, and especially regarding DC fault behavior. With some clever DC converter topologies, we can avoid that the converter feeds the fault into the DC network from the AC side, but we still would need breakers to isolate the faulty lines. So In the end, I believe the dynamics can be decoupled fast by the power electronic converters. For the control, for now, the direct voltages is our only variable, and we will need communication. This will be a super grid, but it will be also a smart grid. And as Adrià put it, in smart grids, you will need communication layer. Stability behavior, it's not that worry in principle if we can apply the reinforcements that the AC grids need and increase a little bit of the inertia that will be lost because of the DC network. For system integration, Europe is different than US, Brazil, or China, for instance. I think Europe is doing research on multi-terminal DC networks much before other countries, but China was actually the first one to go out there and build a 3-terminal system, then they build a 5-terminal system. Why? Because the Chinese can embrace an integrated system architecture. They can go on and build the converters, the controls, the cables, the financing, they have everything local. So that speeds up the development. In Europe, that will not be possible, I believe, so we need to embrace a modular architecture and get all the actors to talk and speed up the development of these grids. And in the end, fault behavior, very worrying, but there are some prototypes of DC breakers already under study. They need to improve a little bit on the voltage rating, but the current rating seems to be approaching what we will need for future multi-terminal DC networks. So I'm sure that by the end of this decade, if not the next decade, we will start to see multi-terminal DC networks in Europe as well. Thank you for your attention.
Thank you, Rodrigo. A question from the floor? Yeah, we have here one.
I read among all the features / benefits of the network that there is also market analysis. What do you exactly mean with that?
With the market analysis, people are looking at how, once you connect these offshore wind farms together, how can you actually dispatch them as a normal power plant? So we are foreseeing that there will be maybe an offshore market where the offshore wind farm producers can say in the next 15 minutes or in the next hour, I will be producing this amount of power, and then can go to a market and sell that power. So this is more or less what we mean into a market for the North Sea Transnational Grid. On top of that, this market will probably have to be integrated to the existing European countries market. And the problem here is that today there is not a single approach for a market for wind energy. Let me explain. For instance, in Germany, they work on an hour basis, and in the Netherlands, they work in a 15-minute basis. So that means that, for instance, Dutch farms can much better provide, for instance, auxiliary services than German farms. But in Germany, they are only rescheduling the power system in an hour basis and not 15-minute basis. So that means that there's less stress on the operation of the system. It's simpler. So we will need to converge into either a single European market or at least a market for the North Sea Transnational Grid.
Do you also think that this network can be used to and as a bidirectional analysis? I mean, not only from the market to dispatch and correctly regulate the wind farms, but also to understand how the market is going in order or not?
I guess that's a bit outside my expertise. I'm not sure how can the North Sea then influence the markets. I'm guessing that more we will adapt to the markets rather than influence the markets.
Thank you.
Okay, thank you, Bel.
Absolutely.